Hello everyone, this is Professor Roman. Let us continue the ring theory lectures. Another key property that shapes the nature of ring theory is the presence of divisors of zero, more commonly called zero divisors. Here is the formal definition. Let R be a ring. A non-zero element A in R is a left zero divisor if there is a non-zero x in R for which AX equals 0. A non-zero element A in R is a right zero divisor if there's a non-zero x in R for which XA equals 0. A zero divisor is a non-zero element that's either a left or a right zero divisor. And we'll denote the set of zero divisors in a ring by this notation, ZERODIV of R. I am not aware of any common notation for the set of zero divisors in a ring, so rather than try to pick a symbol, I decided this would be at least a notation that would be clear to all readers. A non-zero element A in R that's neither a left zero divisor nor a right zero divisor is called a regular element. Of course, for a commutative ring, left zero divisors are right zero divisors and conversely, and so there's no need for the left-right modifiers. Here's an example of a non-commutative ring R in which there exist right zero divisors that are not left zero divisors. Recall from an earlier example that we considered the set of all real sequences. This forms a ring under component-wise addition and multiplication. And let R be the ring of all functions from S to itself. Let lambda be the right shift function, which we talked about before, and let tau be the function defined this way. In words, it just turns all of the elements of a sequence except the first one into zeros. Then tau rho applied to any sequence is tau applied to this sequence, because rho has shifted all the elements over to the right and stuck a 0 in front. Now when you kill all the other elements except the first one, you turn them all to 0, you get the 0 sequence. So tau rho is 0 on all sequences. It is the 0 map. So rho is a right zero divisor, and tau is a left zero divisor. However, for any lambda in this ring, the equation rho lambda equals 0 is the same as saying rho lambda applied to any sequence is the 0 sequence. But this tells us that a right shift of lambda applied to any sequence is the 0 sequence. But when you right shift, you move all the entries of the sequence over by 1 and you stick a 0 in front. If that's 0, then the sequence was 0 before you applied the right shift. So rho lambda applied to any sequence equals 0 implies lambda applied to that sequence is 0. So rho lambda equals 0 implies lambda equals 0. And therefore rho is not a left zero divisor. This example, of course, relied on the non-commutativity of this particular ring. But the example notwithstanding, there are non-commutative rings in which all right zero divisors are left zero divisors, and conversely. And this happens in a matrix ring, for example, Mn of R. So this is a real matrix ring. If A is a matrix in this ring and it's a zero divisor, a right zero divisor, then there's a non-zero matrix B for which BA equals 0. And from that it follows that A is singular. Conversely, if A is singular, then its rows are linearly dependent, and so there's a non-zero vector V in Rn for which VA is 0, and we can define a non-zero matrix B by using, with the property that each of its rows is the vector V. And then BA will be 0. So we've shown that A is a right zero divisor if and only if A is singular. And a similar argument shows that A is a left zero divisor if and only if A is singular. So the left zero divisors are the same as the right zero divisors, and they are the singular matrices. Let's look at this example. We've seen that the units of the ring Zn are the integers in Zn that are relatively prime to n. Okay. So the non-units are the elements that are not relatively prime to n. So this is Zn star. Now, if R is not relatively prime to n, then there's an integer somewhere between 2 and n that divides both R and n. So R is a multiple of x, and n is a multiple of x, where A and B here are in Zn. And so in Zn, we have RB equals AXB equals AN equals 0. So R is a zero divisor in Zn. So the zero divisors of Zn are precisely the non-zero non-units of Zn. Therefore, we can decompose Zn into a disjoint union of 3 sets: the units, the zero divisors, and the zero vector. And this is the symbol we use for disjoint union. These sets are disjoint, pairwise disjoint. So this example shows that, at least in the finite commutative ring Zn, every non-zero element is either a unit or a zero divisor. And that is, in fact, true for any finite commutative ring. And here's the statement of that theorem. As to proof, of course, if R is the zero ring, then the result is clear. Otherwise, we first need to show that these two sets are disjoint. If R is a unit, then we need to show that it cannot be a zero divisor. So if xr equals 0, we write x equals xr R inverse, which is equal to 0 R inverse, which is 0. And so x must be 0. So whenever xr is 0, x is 0, therefore R is not a zero divisor. So there's nothing in common between these two sets. So this is, at least we know now that this is a disjoint union. And to see that it's equal to R, suppose that we take a little r in R, a non-zero element. Now since the ring is finite, we can write all the elements thusly, and we multiply all the non-zero elements by R, we get this set of elements. Now, if R is not a zero divisor, then none of these elements is zero. And so one of them is the identity. R AK equals 1 for some k. And so R is a unit. So if it's not a zero divisor, for every element R in the ring, if it's not a zero divisor, it's a unit. I'm sorry, I should have said for every non-zero element in the ring. If it's not a zero divisor, then it's a unit. And I'm going to leave it as an exercise to explain why this theorem fails for infinite rings. There are infinite rings in which there are elements that are non-zero elements that are neither units nor zero divisors. Aside from units and zero divisors, both of which we've taken a fairly close look at. We talked about units in the previous lecture. We talked about the product of units and the product of a unit and a non-unit and so on, and similarly for sums. And we've just been discussing zero divisors. There are two other types of elements that are of special significance in ring theory. Here is the definition. Let R be a ring, and element A in R is nilpotent if A to the n is 0 for some n bigger than or equal to 1, some positive integer exponent. And the index of nilpotence of A is the smallest positive integer n for which A to the n is equal to 0. An element A in R is idempotent if it's equal to its own square. So examples, in the ring Z6, we can just write out the squares of every element, and we can see that 0 is nilpotent, is idempotent, 1 is idempotent, 3 is idempotent, and 4 is idempotent. In the matrix ring, MNR, any upper or lower triangular matrix with zeros on the main diagonal is nilpotent. And I'll leave that for you to prove as an exercise. If you did take the linear algebra course, you might recall that this came up towards the end of the course when we talked about canonical forms, Jordan canonical form, and so on. An interesting feature of nilpotent elements is given here. If A in R is nilpotent, then 1 minus A is a unit. And that's easy to prove. Let's say A has index of nilpotence n, then when we multiply 1 minus A by the sum of these powers of A, there's a lot of cancellation. We get 1 minus A to the n. A to the n is 0, so we get 1. Therefore, 1 minus A is invertible. And you can do this on the other side as well. As I mentioned in the introductory lecture to this course, it's customary in elementary ring theory to study several different special types of, in particular, commutative rings. And I'm going to define two of these special types now so that we can talk about them and save the others for later. But I want to make a comment first that may, at this moment, seem unrelated. It's a sort of a trivial little thing. If R is a ring, and if the two identity elements, 0 and 1, happen to be equal, 0 equals 1, then for any element A in the ring, we have A equals A times 1, which is A times 0, which is 0. And in other words, the ring is the 0 ring. And conversely, of course, if R is the 0 ring, then 0 equals 1. So there are two things here that are equivalent. You can say that R is a 0 ring, or you can say that 0 equals 1. Those are equivalent. And therefore, if R is non-zero, if and only if 0 is not equal to 1, which is almost always true. The only exception is the 0 ring, which is kind of good. And so in the definition of an integral domain, we're going to give next, and a field, some authors will say part of the definition is 0 is different from 1. Others will say the ring must be non-zero. And so now you know those are saying, they say the same thing. Just two different ways of saying the same thing. A non-zero commutative ring R is called an integral domain if it has no zero divisors. And another way to say that is to say that the product of any two non-zero elements is non-zero. The polynomial ring, f square bracket x, is an integral domain as long as f is a field, so there are no zero divisors. Because the product p of x, q of x equals 0 will imply that one or the other of these polynomials has to be 0. Fields are special types of integral domains. A non-zero commutative ring R is a field if every non-zero element has a multiplicative inverse. Or equivalently, if the non-zero elements of R form an abelian group under multiplication. So a field is a ring in which the operation of multiplication is almost as strong as that of addition. Where it differs is that all elements of a field F have negatives, additive inverses. But not all elements of a field have multiplicative inverses. There's one exception, the 0 element. All the others do. So there's not a symmetry there between the two operations. Addition is still stronger than multiplication. And this does have a profound effect on the nature of fields and field theory. While there's all these common themes in linear algebra, group theory, and ring theory, some of them kind of disintegrate when we get to field theory, which we will do in the next course. Every field is an integral domain because all the non-zero elements are units and therefore they are not zero divisors. The converse fails except that finite integral domains are in fact fields. And there are different ways to prove this. One way is to take an element, non-zero element of a finite integral domain, and show that it has an inverse by looking at consecutive powers. They can't all be different if the ring is finite. But we have at our disposal a tool, a powerful tool, Theorem 131, and that is because we have a finite commutative ring, we can decompose R into a disjoint union of these three sets. Well, since R is an integral domain, there are no zero divisors, so R is simply R star union set containing zero, which tells us that every non-zero element is a unit. And so we have a field. And this is the elegant proof. For the finite ring Zn, we have this decomposition. It's a finite commutative ring. And so this is a field, Zn, if and only if this set of zero divisors is empty. But these are precisely the non-zero elements of Zn that are not relatively prime to n. So there are none. Zn is a field if and only if there are no elements that are not relatively prime to n. In other words, if and only if all elements are relatively prime to n. These are the non-zero elements. For them to be relatively prime to n, that will happen if and only if n is prime. So, the ring Zn is a field if and only if n is prime. This is a very famous theorem. The existence of zero divisors in a commutative ring is related to cancellation in the ring. In group theory, we know we can cancel because every element has a multiplicative inverse. A commutative ring, we'll say that a commutative ring has cancellation if for all elements a, x and y in the ring, ax equals ay, a not zero implies x equals y. So we can cancel any non-zero element. Another way to say that is to say that a times this quantity x minus y 0 implies x minus y is 0 for all ax and y. Now, x and y are ranging over the entire ring, then so is x minus y. So if I call that z, then this is the same as saying a z equals 0 implies z equals 0 for all z in the ring. And that means that there are no zero divisors. And so R is an integral domain. So a commutative ring R has cancellation if and only if it's an integral domain. And this is something that you should think about until it seems rather clear that that's the way it should be. As with vector spaces and groups, if R and S are rings, then the Cartesian product, R cross S, is also a ring under component-wise operations. Component-wise addition, component-wise multiplication. This ring is called the direct product of the rings R and S, and we'll use this notation here, this product symbol with a circle around it. These products fail in the case of fields. The direct product of two fields is a ring, but it's not a field in general, or ever, actually. Okay, subrings. If you've taken my courses in linear algebra and group theory, you're quite familiar with the idea of a substructure. A subring of a ring R is a non-empty subset, S of R, that is a ring in its own right under the restricted operations on R. Or put another way, that inherits all of the ring structure from its parent. Now that includes the binary operations, the unary operations, and the nullary operations, the whole structure. And we use the same notation here that we used for group theory and for vector space theory, and we use this notation for proper subring And we'll write the family of all subrings of R as sub R, just as we did sub G for the subgroups of a group G and sub V for the subspaces of a vector space V. This is partially ordered by set inclusion. Now, as it was with groups, one does not need to check inheritance of all of the ring properties. Specifically, associativity, distributivity, and commutativity, if R is commutative, will hold in S simply because it's a subset of R. Same elements. In fact, closure under addition and negatives, those are the additive inverses, guarantees that S is a subgroup of R, and it will be abelian. Okay, so it's a commutative subgroup of R. Then closure under multiplication and the multiplicative identity will guarantee that S is a subring of R. So here's the theorem. A non-empty subset S of a ring R is a subring of R if the following hold. Now, this is not the definition. This is a characterization, a practical characterization. This is how you would go about showing that a subset was a subring. It would have to be a subgroup of the additive group of R, so it would have to be closed under addition and additive inverses. So another way to say that is closure under subtraction. 0 will be in S. It will follow from this. S has to be closed under the product and under the identity, meaning that the identity is in S. Here's a very interesting example of that shows how careful you have to be when you check whether something's a subring or not. Let S be the subset of the matrix ring M2 of R, consisting of all matrices that look like this. So there's an element A in the first entry and all the rest are 0. Call that M sub A. So S is the set of all matrices M sub A as A ranges over the real numbers. This is a ring under matrix addition and multiplication. In fact, although we haven't discussed this formally for rings, it should seem fairly clear that S is just isomorphic to the ring of real numbers. But, and here's the rub, the multiplicative identity in S is this matrix, M1. And that is not the multiplicative identity in the parent ring, M2 of R. That would be the identity matrix. That would have ones in both diagonal locations. So S is a ring under the same binary operations as M2 of R. In fact, it inherits all of the ring structure of M2 of R, the unary structure as well as the binary structure, and the additive nullary structure. The only thing it doesn't inherit is the multiplicative identity. So it's very close to being a subring, but it's not a subring. It fails to inherit one property, one structure property, and that's a multiplicative inverse. Now, just as the family sub G of all subgroups of a group G and the family sub V of all subspaces of a vector space V are intersection structures, that concept we've used at length in both the previous two courses, but it's included in an appendix to this book if you need to review that. This is also the case with the family sub R of all subrings of a ring R. It's an intersection structure. And as such, sub R is a complete lattice where the meat of a family F of subrings is its intersection, and the join of the family F is more complicated. It's not the union. We discussed that at quite a bit length for vector spaces. If you may recall, the union of, let's say, a finite number of subspaces of a vector space is never a subspace, except in the trivial case where one of those subspaces contains all the others, so the union is just that one subspace. But it is always true that the join of a family of subspaces, subgroups, subrings is the intersection of all the upper bounds for the family. And that looks like this. The join of F is the intersection of all subrings of R that are upper bounds for the family. And this notation we've used before means that A is contained in S for all elements A in the family F. Just as we did for vector spaces and for groups, we can define the subring generated by a subset. Let X be a non-empty subset of a ring R. By definition, the subring generated by X is the smallest subring of R that contains X. And the beauty of the fact that sub R is an intersection structure is that we know immediately that the subring generated by X always exists. It's nothing more than the intersection of all subrings of R that contain X, of which R itself is 1. So it's not an empty intersection. We will denote the subring of R generated by X by double square brackets around X and subscript R if we need to mention the ring. I don't think this is standard notation, but it seemed reasonable, so I'm going to use it. I don't know that there is a standard notation for this. I don't want to use angle brackets like I did for vector spaces and groups because we've got something else in mind for that. Now, again, as in the case of vector spaces and groups, this is an existence discussion. We know this sub widget generated by the subset exists. But we'd like to know what the elements look like. We did that for vector spaces. They're linear combinations of elements of X. We did it for groups. And to do it for rings, we need the concept of words over an alphabet. So let's review that. Let X be a non-empty set. A finite sequence, x1 through xn, of elements of X is called a word or string over X. And it's usually written without the commas and the this punctuation, just using juxtaposition. And you may need parentheses if some of these individual factors are complicated. You can always use parentheses to improve readability. The set of all words over X is commonly denoted by X star, and so that's what we will use, and X is called the alphabet for X star. Here we do have a collision of notation because if R is a ring, R star is the set of units. So you will have to unravel the meaning of the star based on the context. Okay. The number of elements in a word is called its length, We use len of w for the length. There is a unique word of length 0, and it's called the empty word and denoted by epsilon. A subword or substring of a word is a subsequence of w consisting of consecutive elements, and I emphasize consecutive elements of w. A subword that's not equal to the whole word, which is a subword of itself, is called a proper subword. And finally, the empty word is considered a subword of every other word, or of itself, in fact. Okay, now we can get down to business. What do the elements of the subring generated by X look like? Well, this subring is closed under addition, multiplication, subtraction, contains the identity, and it contains everything in X. So it's got to contain all the words in X, as well as all the sums and differences of such words, and, as I said, the identity element. So, for example, if X, Y, and Z are in capital X, then this little guy belongs to the subring generated by X. Now, let's note a couple things about this. First of all, there's some abbreviations going on here. 4 is an abbreviation for 1 plus 1 plus 1 plus 1, a welcome abbreviation. And 2yx is an abbreviation for yx plus yx. So we will allow integer coefficients, and now we understand what they mean. An important thing to note is that these look like polynomials in X, but unlike the commutative polynomials we're used to, here we don't necessarily have commutativity, and so yx and xy may not be the same. Okay? So these are called non-commutative polynomials in X if the ring is not commutative. Okay. And we can use that term. In a sense, it means, again, I think we've encountered this before, it means it might be commutative but might not be polynomials. Okay. After all, some elements may commute, even in a non-commutative ring. If X is a non-empty subset of a ring R, then the subring of R generated by X is the set of all non-commutative polynomials over X with integer coefficients. And again, I'll say, by non-commutative, we mean not necessarily commutative. We're going to devote a later chapter to the study of the structure-preserving maps between rings, known as ring homomorphisms or ring maps. But just as we did for groups, and I think for vector spaces as well, we want to introduce these important functions relatively early in the course so we can use them. And we'll do a more detailed study later on. Now, just to go back to group theory, recall that a function f from G to H between groups here is a group homomorphism if it preserves the group structure, and that's the definition. It has to preserve all of the structure. But as it happens, it's sufficient for f to preserve just the group product. So that looks like this. Then it will preserve also inverses and the identity element. In other words, the entire group structure. just to see that the identity is preserved, we can just write f of 1 equals f of 1 times 1, which is f of 1 times f of 1. Canceling f of 1, we get f of 1 equals 1. So f preserves the identity. But for rings, preservation of both binary operations, addition and multiplication, is not sufficient to guarantee that the multiplicative identity is preserved, because arbitrary rings lack cancellation. And so even though, again, preservation of multiplication gives us this, we can't cancel f of 1 in general. So we have to include preservation of the identity in the definition of a ring homomorphism. So it looks like this. R and S are rings. A function sigma from R to S is called a ring homomorphism, or just a homomorphism, or sometimes a ring map. I tend to use that terminology myself. If sigma preserves addition, multiplication, and the multiplicative identity. And just as with vector spaces and groups, there's a whole slew of terminology here. Epimorphisms, monomorphisms, embeddings, isomorphisms, endomorphisms, automorphisms, and I'll let you read through all this. They have exactly the same meaning as they did in the other cases. A ring map sigma from R to S, being a group homomorphism, preserves the additive identity 0, as well as additive inverses and negatives. But it does one other thing that you don't have in the other cases, or at least it's not meaningful in the other cases. It maps units to units and preserves multiplicative inverses for units. Obviously, it can't preserve multiplicative inverses for non-units because they don't have multiplicative inverses. So if A is a unit in a ring R, then, and sigma is a ring map, then 1 equals sigma 1, which is sigma A inverse, which is sigma A inverse, and also we can do this the other way. Here we can interchange A and A inverse and then swap these two factors. And so sigma A inverse is a two-sided inverse of sigma A. So sigma A, then the inverse is the same as sigma of A inverse. Okay. This is interesting. If R and S are non-trivial rings, then the zero map that sends every element of R to the zero element of S is not a ring homomorphism. It does preserve addition and multiplication, but it doesn't preserve the multiplicative identity, except in the zero ring. That's why I said non-trivial here. So that's another price we pay for requiring multiplicative identities, a small price. One of the most important ring homomorphisms is evaluation. So for example, if F is a field and A is an element of F, then the map epsilon sub A from the polynomial ring f square bracket x to f, defined in words by evaluate at A. In fact, that's what this is called, evaluation at A, is a ring homomorphism. Kernels of ring maps play just as important a role in ring theory as kernels of group homomorphisms, do in group theory, or kernels of linear transformations, do in vector space theory. The kernel of a ring homomorphism, sigma from R to S, is the subset consisting of all elements of the domain that are sent to 0. So the kernel of the evaluation map, then, is the set of all polynomials for which P of A is 0. In other words, all polynomials that have root A. Just as with groups and vector spaces, it's possible to tell whether a ring homomorphism is injective from its kernel. And I leave this for you to prove. A ring homomorphism, sigma from R to S, is injective if and only if its kernel is trivial.